everyone. Thank you so much for joining us for our session. I'm here to introduce our wonderful speaker, Akil Hamam, and I'll go ahead and head over to you.
Thanks, Mary. Hey, everybody. How's it going? Thank you so much for being here. Today, I want to talk to you about Agentic GraphRAG, more specifically, a multi-agent approach of creating knowledge graphs. This is something that my team and I have developed as a workflow because we've been doing a lot of research and a lot of team members are storing their data across, cloud folders and in their own personal folders. And there was no way for us to find the data and look at what we're researching. And so this tool is something that we've created, and it's obviously evolving as we speak, but I wanted to share this with you, get your thoughts on it, and hopefully you can also implement this within your teams as well. So today's agenda, I want to talk to you about the current challenge that we're facing, the architecture overview, with the data extraction strategies, and what's next. Because I think this is like version two in this whole app dev that we're doing, and so this is adding to like a broader vision internally for our team, and that's what happens. That's what I want to talk to you about in what's next. So before we begin, I always like to start off the presentation by this famous quote by Fei-Fei Li. Artificial intelligence is not a substitute for human intelligence. It is a tool to amplify human creativity and ingenuity. And this is something that I always go back to as an anchor because, yes, AI is cool, but if it doesn't help us improve our workflows and make us more efficient, I feel like it wouldn't be of no use to us, right? So this is almost like a grounding anchor. Okay, so let's look at the current challenge that this is again this is what we're facing, and I'm sure different teams have different kinds of problems that they're facing, but this is internal to us. And so the first one is unstructured data, right? Fragmented storage. All of the research data lives across multiple cloud folders and personal drives. Scattered notes. Every researcher adds notes based off the data that they've seen, but they live in that particular folder. And so the valuable insights kind of get buried. Redundant effort. And so if one team member does some kind of research, but then the other team member would have to look at the notes and may also have to look at the data. So you're kind of, duplicating the work over and over again. And also disconnected context. Notes and data are not linked together. And so it's hard to find which of the research paper that the notes were made from. So just to give an example, like every researcher uploads, and again, this is internally, right? So my team, the researcher uploads the data sets and notes into separate folders. And so as a result of which the insights kind of tied to the individual files, stay tied to the individual files. And this makes it difficult to connect the findings. And also to trace a single idea, you almost have to go back through multiple different research papers that we would have read, and not just research papers, like Excel files, data sets that we would have initially combed through to get to this point in the first place. And so and even though every researcher would find relevant data, but they would save it in separate folders just so that they're trying to organize this whole thing. And so the notes and observations are kind of stored in the same folder as the data. And over time, each folder becomes its own mini knowledge base, right? Because you're kind of adding more notes to the same folder. And so when the team meets, we discuss findings, but the insights kind of remain scattered across the folders. And so this is the challenge that we were facing when we started this whole process. Let's look at what the architecture that we're proposing. And so the architecture that we're proposing, and this is the core of what we're proposing, is we start with user uploaded PDFs, and it can be any kind of data set, PDFs, research papers, Excel files, JSON tables, JSON formatted tables, any kind of data set. And that is put through the pipeline. And this is the multi-agent pipeline where we have 4 agents, and one agent identifies entities and relationships. The second one kind of extracts the entities and relationships from the data. The third one merges them because sometimes we have duplicates when we are kind of chunking the data across the board. And finally, the fourth one is a QC check, which kind of optimizes the graph before then being pushed to Neo4j for persistence. And finally, all of this is connected to a chatbot. And in our case, we use the latest OpenAI's ChatKit with the help of Neo4j's MCP server to then help us query the database based on the research that we're doing. So this is an overview of what we are using in our app, at least, and that's what we're proposing. In terms of the tech stack, this being a web app, we use Next.js and TypeScript with Tailwind CSS and Chat and UI. The AI layer is GPT-5. Oh, before that, I almost forgot. All of the multi-agents is also wrapped with Langsmith tracing. So any kind of agent any kind of step that is taken by an agent, we can evaluate it on the back end with the help of Langsmith. So that way we can control the output based on the input that's coming in, maybe change the prompts of each of the agents to help fine tune it better. And so all of this is wrapped with Langsmith tracing. And so the data layer in the tech stack is Neo4j. So now that we've looked at the current challenge and we've looked at the architecture that we're proposing, let's dig a little bit deeper, right? Let's look at the solution. So this is how the web app looks like for us, wherein you have wherein the researchers can drop in their PDFs of any kind of data sets. They can either define what they're studying to get an AI suggested list of entities and relationships, or the user can define their own entities and relationships that they want the agents to look for in the data. And then finally, you can process this, and then after which we can look at what the graph looks like on Neo4j. So the first step in this whole process is user input. In this, the researchers uploads the documents or data sets into the system. They define what kind of information that they want to extract, entities, concepts, right, or relationships. And AI, and so there are two options that we added into this whole thing, which is one, we as a user can define the entities and relationships that we're looking for, or we can define the area of research and give it to the AI analyzer, which will then suggest some nodes and entities. But the first step starts with adding data to the database. So the idea is that the more we do research on a particular domain and the more data we accumulate, all of that can be dropped into this particular web app. And so the graph keeps expanding based on what we're researching. So they're all living in one location. So one of the agents, and the first agent is an analyzer agent, which is when the user puts the PDF or any data set inside, they can either rely on what the agent thinks should be the entities and relationships. So they can put in what the research focus is and get AI suggestions. In this, there were two ways or two directions that we could have gone in this particular agentic approach. Was we could have taken the data that's been uploaded by the user and then taken the research focus and then made the AI to compare, like look into the data and then suggest the LLMs. But we felt that was a little bit redundant just in this initial versions of the app. So what we're doing in this case is we're just defining the research focus or the area of focus that we're looking into, and based off of that, you have the LLM or the agent that is suggesting entities and relationships. So in this case, you can tell that this was, for an example, I put in the latest research paper that was released by Apple and that was called the Pico Banana 400K. And so I asked AI to suggest some entities and relationships. And you can see on the right, you have the entity types and you have the relationship types. And all we have to do is select which ones we want, or we can also add custom entity types and relationships at the bottom. So now that we have, put in the data, and then we have also gotten the entity types and relationships. Some of them are suggested by AI, some, by the user. We go on to the next step, which is, before that, just to give a idea, or just to give a code snippet of what the agent looks like. So we're doing the parsing function for the OpenAI's API, where the output is going to be a JSON output, and that is defined with Zod. So agent one analyzes the research focus and suggests domain-specific entry and relationship types. The researchers can then select, modify, or add any kinds of new entities and relationships. Some of the examples for this particular research paper was image, edit instruction, dataset, subset. And the relationships was has edit instructions or generated by. This is just an example use case, but obviously you can add your own entities and relationships. And then we also, like I mentioned earlier, we have Langsmith tracing for evals. And so every agent behavior is fully observable through Langsmith. We can trace every LLM call from the system and the user prompts to the structured response along with runtime metrics. So this kind of helps us validate the accuracy, compare prompt iterations, and ensure the pipeline stays consistent as we scale across different research areas, right? So as you can tell, with the image on the right, that is the backend eval that we're looking at. And so the output, it also gives you reasoning, and that's based on the Zod kind of definition that we put in. So we wanted entities, we wanted relationships, and also we wanted the reasoning as to why this was used, why these were selected from that particular area of research. Again, just as to eval, so that if we don't like the way it's been done, we can go back in and change the prompts and look at it again. So now we have put in the data. We've chosen the entities and relationships. We've also used the agent one's analyzer to give us some examples and ideas of what we should also look in the data set for. So the next agent is the extracted agent, wherein we take the documents, we chunk them, and then we compare the entity types that we have chosen in step one to what is present in all of these in the research paper. I'll tell you more about it. So this agent essentially splits each document into smaller text chunks for parallel processing. So it applies the schema suggested by agent one, or the custom schema that the user suggested, and extracts information from each chunk independently and simultaneously. So all of these chunks are being processed parallelly. And so this produces a structured output of entities and relationships from each chunk. And what that means is, so in the first step, these were the selected nodes, right? Image, edit instruction, edit pair, and edit operation type. And some of the relationships that came out of step one with agent one was has edit instruction, has edit type, and also part of. So now it essentially takes the chunks. In this case, the PDF that I put in the research paper was divided into 5 chunks of 8,000 characters. And it takes each chunk and then finds out the node with the type. So for example, on the right side, you can see it found out the ID, the type is edit instruction, and the properties. So it's essentially taking the type, the entity type that we want to look for, and it's finding similar content and it's creating a node out of it. And same thing with relationships. It took the relationship, in this case, the type has edit instruction, and it found the target, found the source, and it found the properties. So essentially, we're creating relationships and also entities around our entities and relationships that we want to, based off that we want to find, that we want to research based off our area of focus. And so the code snippet for this agent is essentially this, wherein the GPT-5 extracts entities and relationships. Another thing that in the code, as you can tell, this entire agent is wrapped with a traceable function, and that's how we can trace all of these agentic steps that it takes every single time. And so the prompts and the model with strict guidelines to minimize duplicates, output structured objects, nodes to entities, relationships, links between entities. And so this is the example of this agent's evaluation that's happening in the back end. So we can debug each process chunk to confirm that the correct nodes and relationships were extracted. We can validate the properties and the types of each entity directly from the trace output, and it provides full visibility into each LLM's call, including the input text, the schema, and the output. As you can tell in the image, we have, I think this is, we're looking at relationships in this case. And so you have the source, you have the target, you have the relationship type, and you have a little bit of a description to give us the context of what this whole entity and relationship was. So now that we've gone through five chunks, and which this kind of gives about similar entities and relationships across each chunk, but now we want to kind of merge them, obviously with reasoning, but also merge them to remove any kind of duplicates and consolidate the whole list. And that happens with the entity merger. That happens with the entity merger agent. And so in this case, the agent consolidates any kind of duplicate entities using LLM-based reasoning instead of string matching. So we're just not matching the text of the input schema, text of the entities and relationship across the five chunks. We are essentially taking the description that it comes with, and the LLM is essentially reasoning as to see if they both are along the same lines. If yes, then they're merged. So from the five chunks, we got about 84 entities. Just to give an example, edit instructions, you had ACE++, instruct picks to picks, and instruct edit pairs, and also edit operation type. So like these had almost similar reasoning. And so it kind of, merged all of these, it merged whatever it thought was similar, and it came down to 32 deduplicated entities. Just to give an example, of what the code looks like, again, this is also wrapped with a traceable function from LangSmith. And so it groups all the extracted entities by type, and each group is then sent to the agent to do semantic deduplication based on meaning and formality. The LLM also identify variations that refer to the same real-world entity, and it maps duplicate names to a canonical entity name, right? And all of this is defined in this within the agent as an instruction. And finally, this is what the LangSmith tracing looks like. And so the trace shows how agent 3 merged all the duplicate entities. Now we can open any merge call that has happened, review the raw inputs and the canonical outputs, and even read the LLM's reasoning as to why these entities were combined. And the reasoning, again, is obtained based off of the Zod schema that we have defined, because, again, we want to eval. And another thing that I forgot to explain before was, in this whole process of building this solution for our team, I think eval was the top priority. Yes, we could have built without it, but without having any kinds of eval, the research team couldn't have actually looked at how good the output was and compared it to what their output was when they did it without this app, before when the app existed. So eval is, I feel like, the bedrock of any AI solution that needs to be built out there. And so now we've gone through the four agents, right? The three agents, and then the fourth agent and the final one is an optimizer, which essentially validates and optimizes the graph quality. So agent 4 is a semantic QA quality assessment pass. It removes three relationships. In this case, it removes three relationships that were either reversed or were using the wrong verb. So it kind of looks at grammatical errors. It looks at the description. It looks at everything and finds similarities and suggests that these things need to be removed because it has its own set of reasoning. And so, for example, in this particular run that we did, it removed three relationships, which is Gemini's 2.5 Pro, produced by model, and Nano Banana. It was likely redundant, and the reasoning is what it says was likely reversed or redundant. Evaluation is not equal to production. Then NanoBanana applies edit operation to an MLM-based quality scoring. This is a semantic mismatch. Quality scoring is an assessment method, not an edit op. So I don't know if you remember, in the beginning, we wanted to look for edit operations. And so it still took the initial entities and relationships that we defined, and it's bringing into this and then optimizing this even more based off of our initial entities and relationships that we've defined. And so the last one was, and only relationships were removed. None of the nodes were removed in this whole process. So Agent 4 is essentially the graph quality auditor. It samples parts of the graph, asks the GPT, asks the agent to flag vague or inconsistent relationships in comparison to the defined entities and relationships from step 1, and removes only those with lower confidence. The goal is to not delete data, but to improve semantic precision, keeping the final graph lean and meaningful before saving it to Neo4j. So again, this is also wrapped with the LangChain traceable. And so in this, we can look at the trace for the final event. So every optimization call is recorded, including what data was sampled and what issues were flagged, and the reasoning behind each decision. So this means every relationship removal or node adjustment can be traced, reviewed, and even replayed. And that's the beauty of LangChain. So the level of transparency gives us the confidence that based on what research papers or research data we put in, based on what entities and relationships we define, that the output that came about was what we needed. And I'm not saying it's 100% accurate always, but with the help of evals and us fine tuning the prompt for each of the agents, it kind of gets us closer to being 100%. We only need a little bit of time and effort in the end to now massage the research that we're doing, and that's all possible. It's only possible with the help of LangChain's evals. And yeah. So once we've gone through all the paces, which is starting with the whole PDF entities and pushing it through all the 4 agents, we finally have to push it to Neo4j for persistence. And so in this case, everything we have extracted is cleaned and then it's written into the Neo4j database. In this case, we've used the batch unwind pattern. One query creates all nodes and other groups with relationships by type. So this kind of is almost 10 times faster than the standard inserts, thanks to merge and flexible enough to handle the dynamic schema definitions. So just in this particular example, the write time was about 2 seconds total. Then there were about 57 nodes that were put in, 79 relationships, 4 distinct relationship types for each of those nodes. The write pattern was, like I mentioned, batch unwind plus merge, and it was successfully stored to Neo4j. So, and each relationship type is also grouped for performance. So that makes it faster while in this whole process. So just to give an example of what the code looks like for this final step is it writes all the nodes and relationships to Neo4j in batch using the unwind plus merge pattern, groups relationships by types, and this is the types that we had we had put in the step 1 entities and relationships. So those are what we define as types, and based off of the types, it groups the relationships and entities and then pushes it into Neo4j. Each relationship type is written in its own cipher query for like parallel efficiency, and automatically sanitizes user-defined relationship names, so like uppercase, special characters, and also are replaced. And so now this kind of gives us the opportunity to then use cipher query from the chat kit or any chatbot with the help of MCP server for us to query all of the data and the research that we've done. And the final step is, we kind of hook it up to the chat kit with the help of Neo4j's MCP server. And that's how, and then we start asking questions. So essentially, what we've created is our version of a internal assistant that just takes all the data in, but not all the data from the internet, more so the data that we deem necessary for a particular research that we're doing. So this instant kind of exists for different types of research that happens in different domains. So what's next? So what's next? We have a couple of steps that we're looking to help improve this process even better is domain agnostic. The same the same architecture works across any research domain. And that I think comes from kind of looking at the types of prompts and how can we make the prompts better. But that's just step one. I think step two is also injecting while it's analyzing, while the agents are doing, injecting some instructions similar to how Claude Code has come up with their skills.md. So this is another step that we are planning to add, wherein each agent has its own version of RAG, which it can then look at the things that it needs to dig into, and then does the entity extraction, merging, and optimizing. Graph analytics, I don't think we've pushed how much of Neo4j is being used in this. For now, it's a great way to build the knowledge graph, but I think we want to push it more in terms of data science algos, page ranking, community deduction, link prediction, and similarities across the nodes and relationships. Multimodal extraction, that's a big thing that we're looking into. Right now, it just does text and a little bit of tables, right? But we want to be able to bring in images, videos, and make it multimodal in terms of extracting the data. And also real-time pipeline. This is real-time to a certain extent, but we want to give this workflow the ability to just keep ingesting not just the people or the users putting in the data, but also while we are querying, we can do a query onto the internet and that data goes in as well, and the graph just keeps updating based on the guardrails that we have defined going in. And so I want to end this in, if you have any questions, please, you can enter it in the message box. And hopefully I can answer some of the questions. Or if you think of anything, you can hit me up. This is my website. You can find me on LinkedIn, and then I can help answer any of the questions that you may come across later on.